If you haven't done so yet, pause the video and try to answer the question on your own first before listening on. In part A, the question notes that the rod is both horizontal and balanced. And the word balanced turns out to be a very important word in the context of this problem. When the rod is balanced, that means that the sum of the torques that are acting on the rod will equal 0. And it might be helpful to briefly review the concept of torque from a previous chapter. We know that the magnitude of torque would equal the force multiplied by the distance multiplied by the sine of an angle. Now the angle will be acting between the force and the rod in this case, and we'll see what that means later. Now to proceed, we're going to identify the forces that are acting on the rod. If we look at the left end of the rod, we have a positive charge attached to it, and that is floating above another positive charge. And because both of those charges are alike in sign, they're going to create a repulsive electrostatic force. And so what that means is that on the left end, this charge would experience a repulsive upward force as a result of this positive charge situated beneath it. And for now, we can label that force F1. We also have the weight hanging down on the rod and pulling it down, and that force is already marked with a W. And then on the right side, we have another positive charge above a positive charge, so there's going to be another repulsive force. So the right end is also being pushed upward, and we will label that F2. It turns out also that the bearing is exerting a force, and the reason for that is because since the rod is pressing down on the bearing in response will press upward on the rod. We can call that force F3. In a moment, we're going to see that that force actually will not be necessary, but we'll mark it anyways just for the sake of completeness. Now, we'll move on to the torques. Let's look at the left end, and we're going to be following this equation for each torque. At the left end, we have a force that we have called F1. We will be multiplying that by a distance. Now, the distance will be from F1 to whatever pivot point we decide to choose. And it's probably most logical to put our pivot point right here in the center of the rod, because that would be the point about which the rod would pivot. And so we'll mark that with this blue sphere here. And so the distance that we're looking for, again, is from F1 to that pivot. And hopefully we can see that that distance is simply half of the length of the rod, since the bearing is situated exactly in the center. So the distance we could mark as being the length divided by 2. Now for the sine of the angle, we just look at the angle between F1 and the rod, and we can see that it's a 90-degree angle. So that would be the sine of 90. Let's not forget that the sine of 90 degrees is equal to 1. So we don't actually have to write in the sine of 90 because it won't affect the mathematical result. Now we also want to figure out if this torque is positive or negative. And to do that, don't forget that we have chosen the pivot about this bearing here. So imagine pulling upward on the left end of the rod, and you would see that the rod would rotate in a clockwise fashion. In physics, clockwise is generally assigned a negative sign, so we'll call this torque negative. We'll move to the force that we have marked F3. Notice that that force is passing through the pivot point. Any force that passes through the pivot point will produce 0 torque. So if we wish, we can just add plus 0 into the equation just to remind ourselves that we were technically including it. But again, F3 will produce no torque. We have the W force acting downward, and so we're going to take that W, and we're going to multiply it by the distance from W to the bearing. And that distance is a little bit tricky to see. And maybe we can clarify that by just sort of marking the distance that we're looking for. Remember that from here all the way to where the left end was L divided by 2. And notice the distance that's marked with the letter x. So if we take that distance x and we subtract L divided by 2, which terminates right there, we would end up with the distance that we're seeking, which is right here. So again, if we take x and subtract L divided by 2, that would leave us with the distance that we're looking for. So we'll fill that in for the distance from W to the pivot point. And remember that we have the sine of 90, but that's just 1, so we'll leave it out. We want to decide if it's positive or negative torque, so just imagine pulling downward on the rod where the weight is placed, and you would see that the rod would rotate in a clockwise fashion about that pivot point. And once again, clockwise is negative torque. We can move on to the final force, F2, and we can take that force, F2, and multiply it by the distance from F2 to the bearing, which would be, again, L divided by 2. times the sine of 90, which we will omit. And then F2, if you can imagine, you would be pulling up on the right side of the rod, and that would cause the rod to rotate in an anti or counterclockwise fashion. Counterclockwise directions in physics are positive, so we would put a positive sign here. And then finally, we can set the sum of these torques equal to 0. So now we're going to come up with an expression for both F1 and F2. As noted earlier, F1 and F2 are electrostatic forces. Let's remind ourselves that an electrostatic force is equal to a constant multiplied by the magnitude of the two charges divided by a distance between them squared. So for example, for F1, we would have the following replacement. We would take a constant k, multiply it by the magnitude of the two charges, which is lowercase q and uppercase q, and then divide it by the distance between these two charges squared. And that distance in the diagram has been marked as h, so we would have h squared. And then the rest of the equation will follow. We can drop the 0 here. We'll have the w term. And then when we get over to F2, we're going to also use a similar setup. We're going to have a constant multiplied by the product of these charge magnitudes. We have, in this case, 2q and then uppercase q. So we're going to have times 2q and then the uppercase q divided by the distance between them squared. Now that distance will still be h because the rod is going to be horizontal. So we'll have h squared there. And then we'll multiply that by L divided by 2. And this will still be set equal to 0. Now this 2 right here and this 2 can actually be reduced. 2 divided by 2 is just 1. So we can actually take those out. And now our challenge becomes to solve for x, which is what part A of the question is asking us to do. So let's actually take this term right here and add it over to the right-hand side. And then we can divide both sides by w. So on the right side, it's going to cancel away. On the left side, we have to divide each term by w. So for this term right here, for now, we could just slip that w in the denominator here. And then over here, if we kind of extend this line, maybe for now, we could just put the w right there. So just make sure it goes in the denominator. And then finally, we can add this L divided by 2 over to the left-hand side. And for convenience, we'll stick that L divided by 2 in the far left side of the equation. So we've isolated x. I suppose the next thing and final thing we could do here is just simplify this sort of mess on the left-hand side. And one way to do that would be to find a common denominator between these two terms right here. We can see right now they both have a wh squared. This has a 2, so what we would have to do is multiply this denominator by 2 and then the numerator by 2 as well. So we're basically bringing that 2 back that we had canceled. And then if we look carefully, we can see there's a common factor of L divided by 2 in each of the 3 terms. We'll go ahead and circle them. This one will be a little bit awkward. Right there is an L divided by 2. So we can actually factor out that L divided by 2. And when we do that, we're going to be left with a 1 as a placeholder here. Minus, we'll have the term k lowercase q uppercase q over wh squared. And then we'll have plus 2 k lowercase q uppercase q over wh squared. And then since these are like terms, we can actually combine them. Notice this is a negative 1 kqq and this is a positive 2 kqq. So if we combine those, we'll have a positive kqq. And that's pretty much it. That's about as simple as it gets. Some people prefer to replace their k with the term 1 over 4 pi epsilon. So an alternative way to write this would be as follows. And so all we've done in this case is taken this k and replaced it with 1 over 4 pi epsilon. But either way, these answers are equivalent. Let's move on to part B. And to do that, we're going to revisit the forces that were acting on the rod. Now, be careful here. Part B wants us to find H so that the rod exerts no vertical force on the bearing. We stated earlier that the bearing will be pressing up on the rod, since the rod is pressing down on the bearing. But here the question is telling us that the rod exerts no force on the bearing. So if the rod exerts no force on the bearing, then bearing cannot exert any force on the rod. So we're actually going to take that force out, and the only forces we're looking at then are F1, W, and F2. Let's write out a Newton's second law for those 3 forces. We're going to say that the sum of those forces is equal to 0, again because the rod is balanced. And we can see that we have the two upward forces, F1 and F2. Let's not forget that for F1, we had called that K times Q times uppercase Q divided by H squared. It's pointing upward, so we'll leave it as a positive force. We have the downward W, so we would have minus W. And then we have the upward F2 force, which is going to be K times 2Q times uppercase Q divided by H squared, and we'll set this equal to 0. Now we're trying to solve for H. Let's add the W over to the right-hand side. Let's then multiply each term by H squared. And that way the H squareds will cancel on the left side. On the left-hand side, we are left with those like terms, so that's actually 3KQQ. We could then divide both sides of the equation by W so that it cancels out. And then finally, to solve for H, we can take the square root of both sides. Remember, we square root the right-hand side. H squared will become just H. So we have solved for part B. And again, if you want to replace K with that 1 over 4 pi epsilon, it would look like the following. And so here is an alternative way to express the answer to part B.